All right, today's lesson is on calculating the probability of mutually exclusive events and inclusive events. All right, so let's go over some definitions first. First, a simple event is an event that describes a single outcome. So for example, flipping a coin and getting a heads or a tail. That's a simple event. A compound event is an event that's made up of two or more simple events. So consider if I'm rolling a number on a dice and then flipping a coin. That would be a compound event. Or in this case, rolling a number greater than 3 and rolling a prime number. Those are two separate events, so we call that a compound event. Now, mutually exclusive events are events that cannot both occur in the same trial of an experiment. So for example, if you're flipping a coin and you're flipping the coin once, you can't flip both a head and a tail. All right, so flipping a heads and flipping a tail would be mutually exclusive because they both can't occur at the same time during the same trial. All right, and inclusive events are events that have one or more outcome in common. All right, so let's say we're rolling the number die again. You're rolling an even number and a number greater than 3 if we want to calculate the probability of that. So we have two separate events here, but notice that they have outcomes in common because I can roll an even number, say a 6, and a 6 is also a number that's greater than 3. All right, so the easiest probabilities to calculate are the ones that are mutually exclusive events. All right, so for two mutually exclusive events, that means they have no outcomes in common, right? That during a single trial, both can't happen. The probability, the way we read this in math here, is the probability of A or B. And in math, that symbol right there is also called union. So the probability of A union B is just you find out their probability separately and you just add them together. So you just add their individual probabilities. So for example, I like to draw a picture. We're going to be doing this later. All right, we're going to represent the probability of certain things or counting the number of things in this lesson with Venn diagrams. So for example, here would be the probability of A, and this is the number of ways to do event B. And here's our sample space. All right, so a Venn diagram with a mutually exclusive events would be completely separate. There'd be no overlap. All right, there'd be no shared outcomes between the two events. All right, so if I want to know what the probability of A or B is, then I just add the two together. A plus B, the probability of A plus the probability of B. All right, so let's do an example. All right, so each student in a senior class, right, has voted for a president. And here 25% voted for Hunt, 20% for Klein, and 55% for Villa. All right, so now a student from a senior class is selected at random. Okay, so we're trying to decide, is this a mutually exclusive event or not? So remember, a mutually exclusive event means that in a single trial, that there's no outcomes in common. Two or more things can't happen. So here we're going to select a student. And you're asking yourself, is it possible for a student to vote for more than one of these people? And the idea is no, because a student only casts one vote for one president. Right, so if I'm trying to find the probability, if I'm randomly picking a student and I want to see what the probability that that student voted for Hunt, that's a mutually exclusive event because there's no way that I can pick a student that voted for more than one person. All right, they had to vote for just one of them. And that is different, right? What we're going to find out in a bit from an inclusive event where it is possible that one or more things have outcomes in common. So consider this example for a mutually exclusive event, right? A car is approaching an intersection and it has a 0.1 probability of turning left and a 0.2 probability of turning right. What is the probability that the car will turn? So first we're deciding if this is in fact a mutually exclusive event. All right, and the idea is it is mutually exclusive because a car can turn left or a car can turn right, but a car can't turn both left and right. It's like the same with the coin, right? You can flip a heads or you can flip a tail, but in a single trial, you can't flip a head and a tail. All right, so this is mutually exclusive. So to figure out what the probability that the car will turn, that's the probability of A or B happening. All right, or probability of A union B. So we just figure out their individual probabilities and add them together, and they're already given to us. All right, so we just add up those probabilities, and the probability the car will turn then is 0.3. All right, so take a moment and see if you can figure out the probability of this problem. There are 52 cards in a standard deck of cards. What is the probability of picking a king or a 10? And just to give you some background on cards, in case you're not familiar with a deck of cards, right, there are 4 suits. In each suit, there are 13 cards. Those cards are labeled from 2 to 10, and then a jack, queen, king, and ace. All right, so now, since there are 4 suits, that means there would be 4 kings and 4 tens in a deck, and 4 twos, and so forth. Okay, so now what's the probability of picking a king or a 10? All right, so I first decide, is this really a mutually exclusive event? In a single trial, meaning in a single pull of a card, could I draw both a king and a 10? The answer, of course, is no, right? You either can pull a king or you can pull a 10, but you can't pull them both in one trial. All right, so it certainly is mutually exclusive. So to figure out what the probability of picking a king or a 10 is, I calculate their individual probabilities. And the probability of picking a king is just 4 out of 52 because there's 4 kings in a deck of cards. And a deck of cards has 52 cards in it. The probability of picking a 10 is also 4 out of 52. Because again, there's also 4 tens in the deck of cards. So now if I want to find the probability of A or B happening, I just add their individual probabilities together. And I get that it's 8 out of 52, and we could reduce that fraction to 2 out over 13. All right, so the last practice here. A carnival gives a prize to each customer. Upon entrance, each customer receives a scratch-off card that says one of 4 things, either free popcorn, free corn dog, free game, or free drink. A card has a 4 in 15 probability of being labeled free drink and a 3 in 10 probability of being labeled free corn dog. What is the probability that a ticket is free drink or free corn dog? All right, and since a ticket can't be both free drink and free corn dog at the same time, this would be an example of a mutually exclusive event, which says once again that I add their individual probabilities up separately. So the probability of event A, which we're going to call scratching off a free drink, is 4 out of 15. The probability of scratching off a free corn dog, it tells us, is 3 out of 10. I'm going to add those individual probabilities up. All right, and just make sure, just like when you're working with fractions, that you add and get a common denominator. And we can report that the probability is 17 out of 30. All right, so now let's get to the little bit harder one. So mutually exclusive events, once you identify them as mutually exclusive, finding the probability of A or B is easy. Now, inclusive events, it's a little more complicated. It takes a little bit more thinking. All right, because when you have the probability of 2 inclusive events, A or B, occurring, you have to add up their individual probabilities, but then you have to subtract the probability that both occur, what we call the AND or the intersection. All right, so for 2 inclusive events, A and B, this is the formula. All right, so that symbol in the middle there you can refer to as OR, right? We also call that union. And this symbol here, which when we read it, we can say A and B happening. And that symbol in math is called intersection. And it's pretty intuitive why they call it intersection once I draw a Venn diagram here, which I'm going to do on the right. So in this case, we have inclusive events. That means they have outcomes in common. All right, so this would be the probability of A, this circle here. Maybe I should draw the other one in a different color. All right, and this section here is the probability of some B happening. All right, so that's the probability of B. Notice in the middle here, they overlap. That's referred to as the intersection. That's the probability that both of them happen at the same time. So why are we subtracting it in this formula? You might be asking yourself, why am I subtracting out the intersection if I want to find the probability of A or B happening? Well, let's see what happens when I first calculate the probability of B. All right, so A. So that's this circle here. So then I'm going to highlight this entire circle yellow. There's the probability that A happens. All right, now we're going to add that to the probability of B. So I'm going to do that in a different color. So let's make it green. All right, so remember B is this entire circle. Notice that I just colored in that circle, this section in the middle, what we call the intersection, has been both colored yellow when I found the probability of A and green when I found the probability of B. It was colored over twice. So we double counted that intersection. And that's why we have to subtract it away here. All right, so it'd be like me coming in with my eraser and say, okay, I do want to find that whole probability, but I double counted that intersection. So I want to take one of them away. So that's why we're subtracting that intersection there in our formula. So let's give an example of that. Okay, what is the probability of rolling a 5 or an odd number on a dice? Okay, so first I have to decide what type of event this is. Is it a mutually exclusive event or an inclusive event? Well, let's see, do they have outcomes in common? All right. So, or can when I roll the dice, is it possible for both of these things to happen in one trial, in one roll? Well, I can roll a 5, and since 5 is odd, then those two things are inclusive, right? Because I can do both of them in the same trial. I can roll that dice and get a 5 and an odd number because 5 is an odd number. All right, so we're going to pull out our formula, right? To calculate the probability of A or B happening, or A intersection or union B. I'm going to find the probability of A. Okay, so we have to define the probability. What are we going to call event A? We're going to call that rolling a 5. All right, so I'm going to just calculate the probability. There's 1 5 on a die. All right, and there's 6 sides on a die, so the probability of rolling a 5 is just 1 out of 6. Now I'm going to calculate the probability of event B, which is rolling an odd number. All right, so on a die, there's the numbers 1 through 6, and 3 of them are odd numbers. So the probability that we roll an odd number when we roll a die is 3 out of 6, which can be reduced to 1/2. All right, now we have to figure out the probability of A and B, or A intersection B. Right, that means the probability of rolling both a 5 and an odd number. Oops, let's go back here. All right, and that is still just, in this case, if you think about it, 1 out of 6. Because how many ways can you roll a 5 and an odd number? Well, only one way out of a total of 6 possible outcomes when you roll a die. All right, so their intersection is 1 out of 6. And again, if you like to represent that with a Venn diagram, I highly encourage it. I love drawing pictures whenever I can. So you can kind of see where what that intersection should be. So what you would have is the probability, you'd have 2 different probabilities, out of the total sample space, there'd be 6 outcomes, and there'd be only one way to roll a 5. And then there are 3 different ways to roll an odd number, but there would be an intersection right here of where you roll a 5 and an odd number. There's only one of those, right? Only one number there. And the probability of rolling a 5 is 1 out of 6. And the probability of rolling an odd number, how many ways are there to do that? Well, there's 3 ways to do that. All right. So if I were really drawing this Venn diagram, I'm counting the number of outcomes. I would do it like this. Okay, so there's one outcome where we can roll a 5 and an odd. Then two of these other ones would be the event. This is odd. All right, so there'd be two ways to do that. So you would see the Venn diagram represented like this. All right, so that one on the right is an odd number, and this on the here is rolling any number. All right, so in this case, I add these two probabilities together and subtract out their intersection, which is 1 out of 6. And when we simplify this, we get 3 out of 6, or a half. All right, let's go to the next example. Of 100 divers surveyed, 60 were male and 25 were colorblind. Only 8 of the colorblind divers were female. What is the probability that a diver was male or was colorblind? All right, so we can see that these are in fact inclusive events because I can pick a diver that is male and colorblind at the same time. So that's what we mean by in one trial, right? In one pick. And in this case, both of those things can happen. So if I want to figure out what the probability the diver is male or was colorblind, I'm going to have to use this formula for inclusive events. I'm going to have to find the probability of each of those separately and then subtract away their intersection. And so subtracting away the intersection is where those Venn diagrams are important, which I like to draw. So we'll do it on this one. All right, so what's the probability that we have a male diver? Well, it tells us right here that there's 100 total divers and 60 were male. So the probability of a male being a male is 60 out of 100. All right, so what's the probability that you're colorblind? Well, it says 25 were colorblind. All right, so 25 out of the 100 were colorblind. All right, so now we got to try to figure out the intersection, and this is where we're going to draw a little diagram. So here I draw the box, right? That represents the entire sample space of 100 divers. All right, so here are the male drivers. So I'm going to draw a circle for them, right? And we know that there's a total of 60 in here, right? Because there's 60 of them. Then I'm going to go ahead and draw another circle, make sure it overlaps because I know there's an intersection, right? Because I know it's possible to be both male and colorblind. All right, so I'm going to use this circle here to represent the colorblind divers. And now I'm going to try to fill in the numbers. And this is where it takes a little thinking to figure out that intersection, right? Because that's what we need here. This is the only thing we're missing to be able to solve this problem is what is in that intersection. We figure out how many divers are both of those things, both male and colorblind. And it didn't tell us directly in the problem, but we can figure it out. All right, so the first thing I like to do is to say 8 of the colorblind divers were female. So if here's the set of entire colorblind drivers, I'm going to label this part out here 8. Notice I'm not doing it for the whole circle. I'm not doing it for the intersection. All right, because you can't be both male and female. So obviously here's the female colorblind divers. So that's what it's saying. 8 of the colorblind drivers were female. Okay, now I'm going to go ahead and we can figure out now what that intersection is because right here it tells us that there are 25 total colorblind drivers. So if 8 are female, then that means 17 are male. All right, so I know that this 17 here, remember it has to be in both circles because they have to be colorblind and male. So if 8 are female, that means 17 are male. So that's why they're also in the blue section. So there's our intersection there. And since we have a total of 60 male divers, then 60 minus 17 is going to give me the number out here, which is 43. Right, so now we have the Venn diagram, and we can go ahead and use that to quickly look now at this section in here. So now we know that 17 are both male and colorblind. So that's what we're going to have to subtract out, and that's 17 out of the 100 total. So there's our intersection, 17 out of the 100 right, happen to be male and colorblind. All right, so now I go ahead and I add the two probabilities in the beginning together, subtract the third, follow your rules for adding and subtracting fractions. Then we get 68 out of 100. You can reduce that or you can convert it to a decimal. So in this particular case, I'm going to choose to convert it to a decimal. All right, so I'm going to report my probability that way as 0.68 or 68% chance. All right, so take a moment and pause the video and see if you can solve this problem that involves inclusive probability. So I would draw a Venn diagram, right? That'd be the first thing I would try to do when I solve the intersection. All right, so we're going to use our same basic formula for inclusive, calculating the probability of inclusive events. And how do I know it is? Well, let's read it. Okay, so we've surveyed 1,560 students. 840 were seniors, and 630 read a daily paper. So only 215 of the paper readers were juniors. What is the probability that a student was a senior or read a daily paper? So we know they're inclusive events right away because it is possible to pick a single person and have them both be a senior and read the paper. All right, so now let's calculate the probabilities here of the probability of A, right, that you're a senior, because this is what we're trying to find out, senior or read daily paper. So those are my events A and B. Okay, so probability of senior, right? That's easy enough. We can see that there's 840 of them out of 1,560 students. All right, so there's our probability of being a senior. Now let's find the probability of students who read the daily paper. Well, we can read here. It says 630 read a daily paper, and 215 of the paper readers were juniors. All right, so just from the problem, in this case, we're saying that 630 of the students surveyed read a daily paper, so there's 630 out of 1,560. All right, so usually finding those probabilities is easy. Now it's the intersection that can take a little bit of thinking. Right? All right, so I'm going to go ahead and draw that Venn diagram. So here's my entire set, right, or we call the sample space of 1,560 students. I'm going to draw our two circles, one for seniors and one for daily paper readers. All right, so I go ahead and I make them overlap because I know that they're inclusive. I know there's an intersection. All right, so now I'm going to start filling in the numbers. All right, so let's go back to the problem, right? And we can say, how do I get this number? I usually start from right to left here and work across. So right here, it's telling me that 215 of the paper readers were juniors. So notice I stick it out here on this section of the yellow circle for the paper readers. I can't put it inside there, right? Because that would mean they're seniors. But they're not. They tell us they're juniors. All right, so we know that's 215. Now, how can we figure out the intersection? Well, we have that information right here as well. There's 630 total that read a paper. And if 215 of them are juniors, well, now we can just subtract and figure out how many of them must be seniors. Well, that'd be 415. All right, so now we also know the total number of seniors. So we can calculate this number out here. Since we have 840 seniors, I can subtract away that intersection of 415 to get the total. And in this case, if I take 840 and I subtract the 415, we figure out 415. So let's make sure they add up. That's another way to check when you're drawing your Venn diagram. If I add these two numbers together, I should definitely get the 840 seniors because that circle represents all the seniors. If I add these two numbers up, right, I should get the 630 because that's how many read the paper. So that's a way to check that you've done it correctly. All right, so now we can see the intersection here, right? We can see there's 415 that are seniors and read a paper. That's the probability that we need to subtract. All right, so 415 out of the total, right? 1,560 students that were surveyed are both seniors and read the paper. All right, so now it's just the simple formula, right? And just make sure you add and subtract your fractions correctly. You can reduce the fraction at the end or report it as a decimal like I've done here. All right, so here's our last practice. What is the probability of drawing a black card or a 10 in a deck of cards? Let's go ahead, pause the video if you want to see if you can figure that out. A black card or a 10. All right, so again, how do I know these events are inclusive? You just ask yourself, in one pull, right, can both things happen at the same time? Can I draw a black card and have it be a 10? The answer is yes. When you have a deck of cards, you could draw the 10 of spades or you could draw the 10 of clubs. And those are black 10s. So both can happen at the same time. So we know it's inclusive. All right, so I'm going to go ahead and start with our formula for calculating the probability of inclusive events. And calculate the probability of the first event, which is drawing a black card. All right, so I'm asking myself, how many black cards then are there in a deck of cards? All right, so just to remind you of what a deck of cards is again, right? We have 4 suits. 2 of them are black, the spades and the clubs. Each of the suits have 13 cards apiece. So together there would be 26 of those cards are black, and there's 52 cards in a deck. So 26 out of 52 is the probability of drawing a black card, which you also notice is a half. You know, half the cards are black and half the cards are red. Okay, now we're going to calculate the probability of drawing a 10. And in each suit, there's a 10 and there's 4 suits. So there are 4 10s in a deck of cards. And again, there's 52 cards in a deck. So the probability of drawing that 10 is 4 out of 52. All right, now we got to calculate the intersection. So let's think about that. Is what that means here, right? Remember, this is the and, the probability of A and B. So what's the probability that I pick a card and it happens to be both black and a 10? How many ways are there to do that? All right, so, well, there's only 2 that fit that description, right? There is the 10 of clubs and there is the 10 of spades. So there are 2 cards in the deck of 52, right, that are both black and a 10. All right, so this time I didn't bother going through and drawing the Venn diagram, but you could do that again. Sometimes it works to your advantage, and in this case, sometimes you don't really need it. So I'm going to go ahead and add the probabilities of them separately, then subtract their intersection. And we're going to get that the probability of a card being black or a 10 is 7 out of 13.